Hello everyone. So this is the video for July 4th because there's obviously no lecture due to celebrating America's independence. So have a happy day doing just that. In the meantime, this is an online lecture to supplement what we would have covered on July 4th. So remember on Monday we talked about this thing called a Turing machine variant. So what this is, to recap, is it's some model for a Turing machine that has some variant. And what we wanted to show is that this model is equivalent to the standard model. Uh, Basically, if we have a Turing machine that is a variant of the standard model, it can be simulated by a Turing machine of the standard model and the other way around. So in fact, they recognize and decide the exact same languages. And the one we talked about on Monday was this stay put Turing machine, where the Turing machine can either, so let's draw our tape again. If the tape head is here, then it could be either the case that the tape head can move left, can move right, or it can stay exactly where it is. It doesn't have to move. And what we did is we simulated the left and right in the usual way with a machine in the standard model, but recall the standard model doesn't have a stay put transition, and we simulated one of those by moving right and then moving left without changing the characters. So the one I told you to think about at the end of Monday's lecture, if I can spell this right, is this multiple tape Turing machine, or we can shorten this to multi-tape. So instead of having a single tape to work with, we're going to have some positive integer number of tapes, k. And we'll refer to them as the first tape, second tape, all the way through the kth tape. Okay? So the way that the model works, although it doesn't truly matter here, is that the input is going to be initially presented on the first tape. So let's say it's W1 through WN. And all of the other tapes are blank. But of course, if we wanted to at a high level, we can move the input on to the other tapes if we so desire. So the way the model works is that we're going to have k tape heads that are going to move independently of each other. So, for instance, the first tape head might move right, the second one might move left, although we might be in trouble here if we move left. And this one maybe also could move left. So formally, we only need to make a small change to the transition function, which is we're going to be in some single state of the machine, but we have k things to look at on the tape. So instead of just a single element of gamma to look at, we're going to look at k of them. So this just means pick from the set gamma k times, which means all possible ways of looking at symbols on the k tapes. And of course we're going to change state, but instead of a single symbol to write on a single tape, we're going to have k symbols to write on the tape. And of course, now we need to handle the movement of the tape heads. And since they're independent, we gotta pick from the set L, R, and why not? Let's include stay put as well, because we know that it can be converted into one without stay put. And we can pick from that k times. So maybe, for instance, instead of moving left here, which would cause us trouble here, this one will stay put. And the question is, are multiple tape Turing machines equivalent to the standard model? And we showed that multi-tape TM can simulate a TM, because what it can do is just do the simulation on this first tape and just ignore all of the other tapes, just move right on those. But the question, so that's true, but what about the other way? So let's pose this as a question. Can a single tape, I'll make it clearer, can a single tape Turing machine simulate a multi-tape TM? And so remember our simulation idea from stay put. We had to simulate a single transition where it stayed put with left and right transitions. So what does a transition in the multi-tape machine have to do? It has to look at each of the K symbols on the K tapes, and then from that, once it knows this left side information, it can, because the transition function is total, the right hand side is uniquely known. So once it figures out what the K symbols are, then it knows what transition to do. But the issue is here, with a single tape machine, we only have one tape head to work with instead of K of them. And I alluded to this last time, to have an idea where we dot symbols on the tape to indicate where the tape head was before, as if we were simulating the multi-tape machine. So let's just give an example of this. So if we had two tapes, let's say, and they had, let's say, these tape contents and everything else is blank. Let's just say that at the very beginning, and let's just assume we move the contents of the second tape to be 010 instead of blank. Well, the tape heads will be at the beginning of each, so we'll mark them with a dot on them. And by doing this, we'll say that if the input alphabet here is 01 $, then let's say the tape alphabet must include those three, must include blank, of course, but it also includes 0 dot, 1 dot, so that we can indicate where the tape head is. Of course, the tape head can't be on these delimiters because those weren't in the original simulation. So actually, in fact, we can get rid of the $sign there. Actually, no, in here we need it for the input alphabet, so this is correct. Okay, so let's say that this transition, this tape head moved right, and of course this one also moved right. Maybe let's say this one writes a 0, this one writes a 1. Well, what we can do to simulate this with a single tape head is start at the very left-hand side and start just traversing right, looking at what symbols were dotted along the way. So once we get past here, we saw, okay, tape head, tape 1 include, what it saw on tape head 1 was a 1. On the second tape, it will, once it goes past here, it'll see, oh, I saw a 0 there. And now it uses that information as with the information of the state to figure out, okay, now I know what to do. I'm going to transition to this other state, whatever it is, and it's going to write a 0. It wants to write a 0 in the first tape, and let's say move right. Actually, we have it move right. So, but now, once we go past all of this, we're over here. So what we should do then is go back all the way to the beginning, and then using this information here, go back through the string, the entire tape, and then carry out the transition. So what would happen on this first tape head is, since we moved right, this tape will now be a 0, 1 dot, I think. Yeah. So since we... Actually, I forget what symbol I had there. Oh, we had a 0 there. Okay. So it should be a 0, 0, but now the dot is over here because I moved right. For the second one, the dot, of course, will go away and appear on the second symbol. And the 0, of course, will be a 1 because we wrote a 1. So now we are simulating via 2 entire passes of this entire tape a single transition of the multi-tape machine. So let's try to make this a little bit more formal. So let's say that the multi-tape TM has K tapes, and of course remember tapes 2 through K are starting out empty, but the input is on tape 1. So the single tape TM starts off with, and what does it start off with? Well, it starts off with a delimiter at the beginning, just like before, but then it writes the input down to the multi-tape machine there, and then maybe just as a helpful guide, we're going to put a blank character representing what the other K-1 tapes will start with. So I probably should make clear that the number of tapes that we have here is fixed. So I can't add tapes as I go along, which makes this a lot easier to work with, because if I'm adding more tapes, then I don't know how far right I need to go, how many delimiters I need to see. If I know K is fixed in advance, I know how far I need to go. Okay, so that's great. So, and of course, W1 is going to be dotted, because that's where the initial tape head is, as well as dots on all of the blanks all the way through. Not this last one, because the blanks, that's where the last tape head ends. The tape ends. Okay, so you may be wondering, okay, I get the essential idea, but how do I even remember this? And so how you do that is you remember all the size of gamma to the K possible choices of symbols in states. Because K is fixed and the tape alphabet is fixed, then I can actually write in a state all possible ways of doing this. So for instance, if K is 2 and the tape alphabet, just for simplicity, let's just say we only need to worry about 0 and 1. This is not quite correct, but let's just say we only have 2 characters that could appear under the dot symbol. Well, what we do is we have a state, and then we have 2 choices as to what we see on the first tape head, which is a 0 or a 1. So if we see a 0 on one of them, we'll see 1 on the other. But then we may see a 0 or 1 independently of the first tape. So again, we might see a 0, see a 1, see a 0, see a 1. And then we have 4 states. So if K is quite large, this will actually be quite a large number of states. But since it's finite, it actually will be entirely okay here. So once we get down to here, we'll look and say, oh, now I know what the transitions are because at this point, let's say that state, we have seen a 0 on both tapes. So now I know precisely what transition to do because I know what the transition function of the multi-tape machine is. So in fact, we can carry transitions out even in a general way. The only issue is, and in fact this is the only issue, where let's just say we have something like this on a tape and it doesn't matter what's on the other sides, and a dot is right here, and the multi-tape machine decides to move right. Well, this is an issue because if I move right, well, I don't have anything left. So what do? We talked about it last class, and what we do is we shift the entire contents of the tape from here on one position to the right and add a blank symbol there. So we'll add a blank symbol and we shifted everything else right one position. And in the other case, if we have the same scenario, but we have a dot on the left side and we try to move left, then we can detect that and say, if I go left and land on a delimiter symbol, then I'll stop computation because that'll be equivalent to going off the left-hand end of the tape. So in fact, that's all we really need to do at a high level. Of course, if you want to make this a low-level thing, and I encourage you not to do that because it's very tedious, of course there are some other details we might need to check. But at a high level, what we're doing is we're simulating the transition and handling the cases where we may need more tape, and by doing this we're keeping track of what symbols we have seen and where the tape head was on each of the tapes. So in fact, any multi-tape Turing machine can be simulated by a single tape one. Which is pretty cool. So in fact, if you want to use multiple tapes from here on out, you're absolutely welcome to, and then just cite the result. Multi-tape Turing machines are equivalent to the standard model in computational power. Of course, if we use a multi-tape machine, we can have our language be decided faster, or at least as fast as a single tape one can, but in terms of computational power, they are the same. Okay, so one more variant, and so this one is a little bit tricky, but it's maybe annoying to some of you how if we have a state and we want to go to another state, and let's say that this transition involves reading a 0, it's not the case that we can have in the standard model another transition which reads 0. Since the transition function is total, there is exactly one transition for any state and symbol read combination. Here, this is not allowed because now I have two places I can go. But maybe what we can do is we'll allow this possibility. So we're going to be talking about what is called a deterministic Turing machine. And so this is a concept that's not is very misunderstood by people who take this class. And so the notion of non-deterministic is not equal to or random here, or it's not equal to try all possibilities. Because what we could do if we had a situation like this is just try all possibilities and accept if at least one of the ways accepts. So, but it's not quite that. So the formal way of saying what a non-deterministic machine is that if one of these choices leads eventually to Q accept, then the non-deterministic Turing machine, which I'll abbreviate NTM, will make such a choice. And if there is no way to eventually get to Q accept, then it cannot make that choice. Then it'll just make an arbitrary choice at that point because there's no way to have it go to Q accept. So you may think, okay, that's a strange model of computation. Why are we doing that? Because there's no non-deterministic computers according to this definition. There's not like you can run your program and make a choice that guarantees if there is a way to eventually accept, you will make that choice. No such computer exists. But what you can think of this as is some type of certificate that, in its a short certificate of how the machine leads to Q accept. So instead of taking such a roundabout way that may take a really long time to accept a string, it might be doing the right transitions over and over and getting to an accepting, going to Q accept much quicker. And so we'll see a bit of this throughout the class, but it's a way of thinking about how long can a machine run for. Can you make it run for a much shorter amount of time, or do you actually need a long period of time to run the machine? Okay, but another formal way of specifying this is that the transition function, so we're back to single tapes now. So the transition function starts out the same, but instead of having the right hand side be exactly one choice to make, we're going to have the power set of this be the set of all possible ways of going to another state, a number, writing a symbol and going left or right. And so now note that the power set is just a set of all subsets of this right hand side. And so by doing this, it effectively allows us to have as many transitions like these as we want, including 0 if we want to. So it may be the case that there's no transition coming out here that reads a 1. And so if we get to this state and we see a 1 on the tape, then that must mean that the computation stops because I have no place to go. But if I get to that state and I see a 0, then I have two choices. There are two choices effectively the machine can take. So I just want to reiterate, the non-deterministic machine will always make at most one choice. It can make 0 choices if there is no choice to be made. But if there is a choice to be made, it will make exactly one choice. It doesn't try all possibilities. Okay, so now we want to show that non-deterministic machines are equivalent to the standard model. So can a non-deterministic machine simulate a normal Turing machine? And if you think about it, what you do is the normal Turing machine already is a non-deterministic machine in the sense that you have exactly one choice for the transition function. The non-deterministic machine doesn't have to have multiple choices or 0 choices for transitions. It could have exactly one. So in fact, the answer is yes here. It just simulates the Turing machine in the usual way. There's a slight technicality here where, remember, the right-hand side of the normal Turing machine is just this. But if we add the non-deterministic part on top of it, note that this is a set of sets. But the technicality here is that the Turing machine has right-hand side of delta not being a set. So the way to fix this so that it fits the definition of non-deterministic machine is that make right-hand side of delta all singleton sets. And then that way it fits the definition of the non-deterministic machine's transition function. But if you just look at it as a state diagram instead of just the formal way, then in fact any state diagram of a Turing machine is a non-deterministic machine. So that's easy. But now the question that's seems a lot harder is, can a Turing machine simulate a non-deterministic one? And so now it seems like it seems like the non-deterministic machine does have a lot more power, right? Because now we're allowing the machine to make arbitrary some choice that leads to acceptance. But the normal Turing machine has no choice whatsoever. So what could we do here? So the idea here that we're going to pursue is something called a computation tree. And this is a tree that keeps track of what choices can be made. And the normal Turing machine is going to explore this tree. And the tree represents all choices that the non-deterministic machine can make. Okay, so let's just think of it like this. So at the root node, this is the starting config. So each node in this tree is going to be a configuration. Although it doesn't actually truly matter, but you could think of this as configurations. And so the non-deterministic machine may, for instance, have exactly one choice that it could make at the starting config. But maybe once it gets down to this second level, it may have 3 choices or some number of choices it can make. Maybe this first one has no choices at this point, but maybe the next one has lots of choices it can make, and then maybe this other one has 2 choices it can make. Then maybe this one has a bunch of choices that it can make, and then etc. So it's a potentially infinite tree, because the non-deterministic machine may make a choice that has it run forever. Or there may be a sequence of choices you can make that make it run forever. But if at some point there's some node way down here that has QAccept in the configuration, then there must be a sequence of a sequence of choices you can make that have it eventually go down to that node, or some node in QAccept. So the problem is, how do I explore this tree? Well, if I did it in a depth-first search manner, so I'm going to call this a bad idea and you'll see why in a second. If I did this in a depth first way, then we'll be fine for, so I'll do this in blue. So we'll be fine here, and then we see, oh, there's no choice at this second layer on the left, so we'll backtrack up one layer, then go down here, then go down here, then go down here in a depth first way. But as you may see, I might run forever if I do it in a depth first search way. And we don't want that. Even if the machine is the non-deterministic machine is a recognizer, because we want to halt if there is a queue except somewhere in this tree. So this is a bad idea. A better idea, so good idea, is to do a breadth first search. And the way we can do that is we go down in a breadth first search way. So I look at all the nodes that I can reach in the first layer, then all the nodes I can reach from every node in the first layer to every node in the second layer, then every node in the third layer, every node in the fourth layer. If there is a queue except somewhere in this tree, then I must eventually get it because it's at some finite level in the tree. So it may take a long time, but I can reach it eventually. If there is no queue except at any point, well, then that must mean that the machine runs forever. But that's actually okay here because the non-deterministic machine would have run forever anyway because there's no queue except in there. Okay, so in fact, so as a detail, and I'll pose this as a Piazza question, how to actually perform this tree on a normal Turing machine. Because there are some details that need to be worked out in how you actually store these configurations and how to handle when you're finished with a layer and how to move on to the next layer. So I'll let you think about that and we can discuss on Piazza if we need to. Okay, but hopefully the idea is clear. For variance in the general sense. And there's a question on problem set 2 where you have to show whether or not a model of computation is equivalent to the standard model. So you have to show that if you think it is true that a normal Turing machine can simulate that model, a Turing machine in that model, and the other way around. Okay. So, some of the questions that we talked about for example, one of the problems, the do problems on problem set 1 was about this super duper number thing, where we had integers x of the form y to the alpha with some conditions on y and alpha. And what you could do is we wanted to list out the potential values of y and alpha in such a way that I'm going to list the super duper numbers and then just check whether x actually equals one of them at some point. And you may think, well, is there a way that I can just enumerate or list these super duper numbers? Because if there is, then I can just compare it to x and then eventually just check, is it equal to any one of these? And then if I list them in order, if I eventually get higher than x, and I haven't shown that it was equal to x at any point, then x in fact is not a super duper number. But you may think, well, is there a more general way to think of this type of listing out strings? And in fact there is. So we're going to talk briefly about what are called enumerators. So an enumerator is what this is a Turing machine that starts with empty input and enumerates in some sense strings of a language. So, for example, if we have a machine that just lists the members of sigma star, let's say in lexicographic order, or in some order close to that, then we can say that that machine is an enumerator for sigma star. So, for instance, if sigma is 0, 1, so sigma stars all binary strings, then what we could do is list all the strings in sigma star, let's say in lexicographic order. So we start off with the empty string. I'm using pound sign here as a delimiter. So we list empty string, so nothing there, then 0, then 1, then 0, 0, then 0, 1, then 1, 0, and then we can carry on from there. So here, this machine definitely does not halt in a finite amount of time. But what we don't want from an enumerator is for it to just say some string over and over without ever getting to another string. But it's perfectly possible or allowable that we can list strings slightly differently. So let's say I write the empty string once, then I write the 0 string twice, then the 1 string 3 times, then 0, 0 4 times, 0, 1 5 times. So I am listing out the strings in the language, but I'm taking a lot longer than the first one did. So what we want here is that any string W in the language will be eventually, in some sense, printed on the tape. So if I picked string 1001, then for this guy, it may take a really, really long time before this string is printed, but it'll eventually be printed. So this is not a formal statement, and in fact, I don't have to list the members of the language in lexicographic order. For instance, if I list the integers out as, let's say, positive integers as 5, 4, 3, 2, 1, then 10, 9, 8, 7, 6, and I carry on where I shift these 5 sets up by 5 repeatedly. I'm not listing them out in lexicographic order, but I will eventually print any given integer. So if you tell me an integer, this enumeration will eventually print that number. And we say L is enumerable if some TM enumerates it. Okay, so this is a little different than what we're used to, but you may think, well, we have this notion of decidable, recognizable, and now enumerable. So it seems like we have a whole collection of different types of languages. But in fact, we will show that, as a theorem, that L is enumerable if and only if L is recognizable. Okay, great. So let's see. So of course now we have to prove it in both directions, right? So we need to show both directions. So this forward direction is easier. So if I'm given an enumerator can I make a recognizer for the same language? So I have a machine that prints out strings such that any string you like will eventually be printed. Can I do a recognizer for it? So I'm going to stop the video here and then we'll get back into this.